Before we jump into finding internal forces using equilibrium, let's remind ourselves of how to find the system determinacy to make sure we can actually get to those internal forces. If we have a determinate system, we are going to be able to find our internal forces just by using our static equilibrium equations, which we'll review. If it's an indeterminate structure, those equations of equilibrium will not be enough to find the internal forces. We're going to have to resort to some other equations from compatibility. And we'll talk about those later. And when you see the word compatibility, all we're talking about is deflection. We could also have unstable structures, which means we have more equations than we have unknown internal forces, and those structures are unstable because they can see rigid body motion. So let's remind ourselves of the rules for trusses. We have an R and a 2n, and depending on their relationship, we have unstable, determinate, or indeterminate structures. So n is the number of joints, R is the number of reactions, and number of members. And the way to remember these equations, if we take a look at an example, I have a truss with a pin and a roller. So my number of reactions, I have, let's call this AY, AX, BY. I have 3 unknown reactions, so my R would be 3 plus my number of members, because if I cut this member, it has an internal force. Let's call this ACB and AC, right? I don't know that internal force, and I could do the same thing for each of these members. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 internal forces. So I have a total of 14 unknown things, unknown reactions and internal forces. And at each joint, so 1, 2, 3, 4, 5, 6, 7, at each joint, I could write 2 equations of equilibrium. I could write the sum of forces in X and the sum of forces of Y. So this is how many equations I have. I have, in this case, 14 unknown things times 2 equations of equilibrium times 7 nodes, and I have 14. This should just be, is 14 equal to 14? I have a determinate structure. So I could find all of those internal forces just by using my 2 equations of equilibrium at each node. Let's look at another truss with 2 diagonals. And I can check it both ways. I can say it's connected at that middle joint. So I can say that this is a joint, 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 joint. So I have n equal to 5. I have 3 reactions plus 1, 2, 3, 4, 5, 6, 7, 8 internal forces. I have R compared to 2n. 11 is greater than 10. I am 1 degree indeterminate, so I just did 11 minus 10 to get 1. If I have it disconnected at that middle joint, I now have n equal to 4. R is still 3 plus, now I only have 6 members. I still have 9 is greater than 8. I'm still 1 degree indeterminate. So it's not going to matter whether that joint is connected or not. I'm going to see the same degree of indeterminacy. What if I take that same structure and instead I change the boundary conditions to 2 rollers? So we'll do the second case, the not connected. N is 4. R is still plus 6 members. But now I only have 2 reactions. So I have R compared to 2n, I have 8 equal to 8. Alright, so the 8 equal to 8 tells me it's determinate. But the problem is, if I push on the structure, it's just going to move rigidly to the right. Right? It's acting like a skateboard, basically. So even though our equation tells us it's determinate, this is actually unstable. So be careful. If you can see rigid body motion, regardless of what your equation tells you, it is an unstable structure. We could do one last example. I have 3 reactions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. N is 8. So I have 16 equal to 16. I do have a determinate structure. I can't see rigid body motion because this prevents motion to the side and up and down. So that's our determinacy for trusses. Frames, it's going to look very similar, except instead of 2n, we now have a 3n. And the way to remember that one is if we have a beam and we make a cut, we're going to see 3 internal forces: axial, shear, and moment. So this is saying n is basically the number of pieces after we cut for each piece. Right now I have 2 pieces by doing that cut. I can write 3 equations of equilibrium here. I can sum my forces in x, I can sum my forces in y, I can sum my moments about a point. So I could do that for both of these members. And so my n in this case would be 2. My number of reactions is just like it was for trusses. And now I need to add my number of internal forces and moments, which will always be 3 if I cut a beam. If I cut a hinge, I only release 2, shear and axial. So let's look at some examples. If I have a frame, a fixed connection, and a pin, this says number of pieces after cutting closed loops and hinges. So a closed loop, right now I do not have a closed loop. If I had a member from the fixed support to the pin, that would be closed. Or if I add another story, that would be now a closed loop. This is the closed loop. So I need to cut it, and each place I cut, I release axial, shear, and moment. 3 internal forces at each level. I also have my reactions. Don't forget your moment reaction at the fixed support. It's the most common one to forget. When we make that cut, I have this whole piece and this whole piece. So 1, 2 pieces. So 2 pieces. R is 5, or my internal forces are 3 plus 3. So I have R compared to 3n. It's 5 degrees indeterminate. Take another member. So I start off with a cantilever. This has 3 reactions. So R equals 3. I don't need to make any cuts because there's no closed loops or hinges, so I have a determinate structure. If I add on a support, this is called a propped cantilever. Now n is still 1, R is 4. I'm 1 degree indeterminate. If I then take this structure and add a hinge, now I've got to make a cut. And when I cut here, I release 2 internal forces. So n is now 2, R is still 4, and I've released 2 internal forces. This 2 is because there's 2 pieces, one on either side of the hinge. Compare R to 3n, this is now back to a determinate structure. So adding supports makes our structure more indeterminate. We have more unknowns than we have equations of equilibrium. Adding hinges reduces our number of knowns because we get rid of a moment anytime we have a hinge added to the structure. We can look at a couple other frames. I have a frame that looks like this. If I put pins, base, and hinges in the corners, now I have to cut at hinges. I have reactions, the base. I now have 3 pieces 4 reactions, 4 internal forces. I have 8 is less than 9. This is an unstable structure. And if you push on it, you'll see it just kind of flop over. These can all rigidly move relative to one another. So there's some exceptions to our equations, just like we saw with the truss. If we have parallel reactions only, so like the truss skateboard, right here we have 3 reactions, 1 piece, we would have 3 equal to 3, but this is unstable because we have rigid body motion. So anytime you only see parallel reactions, you can have rigid body motion. The structure is unstable regardless of what the equation tells you. If you have concentric reactions, so if we have the structure that looks like this, all of our reactions point to the same point, so everything could rotate rigidly about that point. This is also unstable. And the third exception, we could have a really big frame, right, with some hinges in it. And if we check the determinacy of this, I have 6 reactions. I'm going to cut my closed loops. So I have 3, 3, 3. A hinge down here as well. So I only have 2. 2 and 2. I have 1 piece, 2 piece, 3, 4, and 5. So I have 5 pieces. I have 3, 6, 9, 12, 15, 18, 21, plus 6. I have 27 internal forces. 33 total. I have a highly indeterminate structure, but if I look at this beam down at the bottom with 3 hinges, this can just rigidly move. This is actually an unstable structure despite all those degrees of indeterminacy.